Hey all, welcome to the sixth episode of Distributed Systems 101 series. So, in this one, we will be talking about concurrency control and distributed transaction. So, first, we'll be covering the distributed transaction, the concepts behind the distributed transactions, and why concurrency control is an essential thing to do while performing a distributed transactions. So, let me quickly write it down here. Okay, let me set the screen. Yeah. Okay, distributed transactions. So what are distributed transactions? So basically distributed transactions are those transactions in which multiple machines are involved. So suppose a transaction can perform multiple operation within it, right? So if a transaction involves multiple operation that involves interacting with multiple machines or multiple systems, then that can be called as a distributed transactions. So suppose if this is a transaction T1, it performs a write on a particular data item X, or we can say X1, and it also performs a write on another data item X2, and then it commits itself. So suppose if data item X1 was present in a different machine, right, and if data item X2 was present in a different machine, then this transaction would be called a distributed transactions, because this will require uh, the the transaction to like interact with different machines to get their job done. So this is like the high level concept of distributed transactions, and we in this lecture will try to understand that why distributed transactions are important and why concurrency control is important, or why do we need to take care of the concurrency control while performing a distributed transactions, and what are the things can go wrong if we don't do that. Now let me take a scenario where we will be focusing on a distributed transaction. So this is how a transaction will look like. So this will be my distributed transaction that will be performing operations on two accounts. So suppose we have a bank, right? And within this bank we have two accounts. Say the account one is X and the second account is Y, right? So what we are planning to do is that we are planning to send or transfer some money from account X to account Y, right? So what we're doing is that we're gonna do a standard transaction which will gonna like take some money from account X and it will gonna deposit that money in account Y. Pretty standard. So the gist here is that the account X and the account Y. So this bank is pretty huge and it has millions and millions of accounts, and that's why this particular account is present in a different replica machine or a different database node, and this particular Y node is present in a different database node. So what we are dealing with here is that we have a distributed architecture or a distributed database system. So we have multiple instances of database globally distributed, and this is, we can say that this is the first instance and this is the second instance. So these are the two instances, and account X is present in one machine while the account Y is present in the another machine. And that is why this entire transaction process will be called a distributed transaction, because we are trying to move some amount of money from account X which is present in one machine, and we are trying to transfer that particular amount of money into the different account which is present in a different machine. Now how this transaction will look like, let me tell you that. So now let's quickly talk about the transactions which we were discussing previously. So there were two transactions here. One was T1 and another was transaction T2. So what T1 will be doing is that, so T1 will start, and after that T1 will gonna add a particular sum of amount. So suppose we are sending an amount maybe T from account X to account Y. So suppose this is account X and this is account Y. Both of these accounts are present in a different machines, right? And that is why the whole concept of distributed transactions. So we are moving say amount T from account X to account Y. So what we are doing here is that we are first adding an amount of minus t, and we are then adding an amount of t, and then we are ending, right? So this is the this is the entire transaction, how it will start. So adding minus t to x means we are withdrawing amount t from the transaction. I hope that makes sense. So I'm gonna just zoom it. Okay, this is good. Just have to. Okay, cool. Yeah. So by adding minus t to account x, it means that we are withdrawing amount t from x, and adding positive t, or simply we can say t, to account y means that we are submitting that account, or we are depositing that amount t into account y. So this is the basic transaction which t1 will perform, and we have another transaction t2 which will gonna perform an audit on these accounts. So by auditing, what it will do is that it will gonna get the balance of account X, it will get the balance of account Y, meaning what was the money which was present in account X, what was the money which was present in account Y. It will gonna sum it up and it will gonna show that. So what it does is that, again, we can have here the transaction will start, and after that it will gonna have one value where it will get the balance of account X. There will be another value where it will gonna get the balance of account Y, and it will print these two values, or it can print the sum of these values as well, and then it will end. Now this T2 transaction is an auditing transaction. So by auditing, what does it means is that it is probably checking something. So by checking means that it will this transaction would want to assure that whatever amount v1 and v2, like whatever the sum of the account, or whatever the sum of the balance in the account X and Y is, stays constant even after the start and after the end of the transaction. So suppose that, for an example, if initially account X has a balance of 10 and account Y has a balance of 5, then suppose we are moving a amount of money, say 2, from account X to account Y, then even after the end of the transaction, then account X will have 8 and account Y will have 7. So even after the end of the transaction, the sum performed by the audit transaction, the sum of the amount of money present in X and Y, that is basically 15, should be constant. So should be the same even before and after the transaction, right? So that is what audit will perform, and going ahead we'll see that how this auditing, or how this transaction uh, can get faulty values for the balance of account and X and Y when this distributed transaction takes place, and why concurrency control helps us to ensure that the sum of the money or the audit transaction gives the correct value. Let's talk about the serializability of these transactions. So by definition, what serializability means is that if we talked about two transactions previously, right? If these two transactions can be performed in a serial order, then we can say that these group of transactions are serializable, right? So what it says is that we had two transactions T1 and T2. So if T1 and T2 can be performed in a serial order, then this will ensure serializability, meaning if T1 is performed before and afterwards T2 is performed, or T2 is performed before and afterwards T1 is performed, right? In that case, they will ensure that these transactions are serializable. Now let's handle the first case where we are seeing that transaction T1 performed first, and after that transaction T2 has performed, right? So what we are trying to do here is that initially, suppose we saw two accounts, right? Account X and account Y. So account X has an amount of say $10, and maybe account Y has an amount of $10 as well. And now what we are trying to do is that let's T be the amount which needs to be transferred from X to Y. So let T be $2. Okay. Now what will happen is that transaction T1 will execute first, And after the end of the transaction, we will have the following configuration, where the value of x will be 8 and value of y will be 12. And that makes sense because we are transferring amount t from account of x and moving it to account of y. So that is why this makes sense. Now we will have another like transaction T2. So what T2 will do, T2, the job of T2 is to perform an audit. So what it will do is that once, since transaction T2 is starting after T1 has completed, so it will gonna print x equal to 8 and y will be equal to 12 as a amount or as the current balance of these two accounts. And that makes sense because like initially the total amount, or basically the sum of the money in x and y was 20, and at the end of T2, at the end of execution of T2, the sum of balance in these accounts is still 20. It means that the audit performed by T2 is correct, or there is no data inconsistency happened. So audit went successfully. Now let's move on to the second case. Now let's talk about case 2. So in this case, instead we are reversing the order of the execution of transactions. So in the previous case, T1 executed first. Here T2 will execute first, and afterwards T1 will be executed. So initially the configuration of the account balance looks like this. So x has amount 10 and y also has amount 10, and we will be transferring an amount t, which is basically $2 from account x to account y. So now what will happen is that the audit transaction will be performed first. So T2 is performed, and since T2 after the execution of T2, the balance of x and y was this. Afterwards T1 performs, T1 is executed. It moves amount of t from account x to account y, and it prints the balance. And after that, the balance of amount, or the balance in account x and y, will look like this, right? And again, this also maintains the data consistency, since the amount, or the total amount initially before the start of these transactions was $20, and after the transaction ended, the amount is still $20. So this is maintained across the transactions, like across the start and at the end of the transaction. And hence we can say that, like, if the transactions happens in the serial order, or if the serializability of these transactions are maintained, then there will be no data inconsistency. Now moving ahead, what we're gonna understand is that how the data inconsistency can happen if we don't perform a concurrency control, or if these two transactions try to take place together or parallelly, then how, and if we do not take care of the concurrency, then how this can go bad, or how data inconsistency can happen, or how we can see some faulty values at our screen. Now let's talk about concurrency control. So since this current situation we are dealing with is a distributed transaction, that is why concurrency control is essential here, right? Because within the transaction we are talking to multiple machines, and we are trying to perform operations over data items which are stored in multiple machines. So if we had two transactions, right, T1 and T2, if these two transactions are trying to happen in parallel, then we need to make some concurrency control, or we need to set some ground rules. And what are these rules are? So basically the first rule is to acquire lock, right? So by saying acquiring lock, we means that we need to, like, whosoever transaction try to execute first, it has to perform lock on all the data items until its completion. So if T1 is executing first, so if this T1 transaction is executing first, then it will gonna, since it is performing operation on data on the account balances x and y, it will perform a lock on account x and y, right, till its execution completes, because like we don't want another transaction to interfere until its execution is going on. And that is why, like, that is the first rule of the concurrency control. We are acquiring lock on these two transactions x and y till the these two accounts x and y till the transaction completes. Now there is one question here, that why do we need to lock both of these data items. So what T2 was doing is that T2 was performing a read from account X and account Y, right? So what do we do? Like, why don't we do one thing, that if the transaction T1 starts executing, and since like transaction T1 was trying to move a particular amount, say T, from account X to account Y, why do we do one thing, that once the transaction T1 has uh, withdrawn a particular amount T from account X, we release the lock from X. So basically, uh, once we have withdrawn a particular amount T from account X, then at that time we release the lock from X so that it can be read by transaction T2. In that case, the wait time can be reduced. So transaction T2 will not have to wait for the completion of entire transaction. Instead, it only has to wait for transaction T1 to perform its operation on account X. And after that, since transaction T1 will release the lock on X, transaction T2 will be able to read it. So this looks like a comparatively good solution as compared to what we saw before, but it has its own bottlenecks, and that's what we would like to see, that like, what if transaction T1 release the lock on data item X in middle of the transaction or before its completion, then how the things can go wrong. So we're gonna see on around two cases where things can go south, or where things can go poorly when we do this. Let's look at the first case where we are allowing the transaction to, or the transaction 2 to read the data item X while transaction T1 is still processing. So we discussed previously that we will allow the transaction T2 to read data item X once transaction T1 is done performing a write or done manipulating it. So let's see this in picture, how we are trying, what we are trying to achieve here. So suppose we have transaction T1 and we have transaction T2. Since both are like running parallelly, and what it is doing is that, so at the first step, the transaction T1 will withdraw an amount T from X. After that, what it will do is that it will add amount T to account Y. And what T2 is doing? So what T2 is doing, T2 is reading values from account X, and after that it is trying to read value from account Y, and then it prints those values. So it's basically print whatever is present in account X and account Y, and this is what like these two transactions are performing. Now what is currently happening is that suppose both of these transactions starts executing, and at this point T2 is behind T1. So T1 reached account X first and it acquired lock on account X. Now it withdraw amount T from account X and it went ahead. Now what we were saying is that once transaction T1 is done with account X, it can release the lock so that transaction 2 can perform a read operation on it. So now what it did is that it released the lock account on account X, and since transaction 2 reached here and it saw that the lock on account X has been released, it successfully read the value from account X, and after reading the value of V1, so suppose initially the account X has a balance of 10 and account Y has a balance of 10. So after reading, account X got a balance of, oh sorry, account X will not have a balance of 10 since transaction T1 has deducted an amount from account X. So at this point account X is, the balance in account X is 8 since the amount of balance we are deducting is 2. So current balance in account X is 8, and this is what T2 reads. But after that what happened is that transaction T1 went behind, or transaction T1 was slow, because since Y is another data is present in another machine, and that machine may be facing some network issues. That is why transaction T1 got slow, but transaction T2 was fast due to some reasons, and transaction T2 went ahead of T1. While T1 was here, transaction T2 went ahead, and since transaction T1 has not reached Y, there is no lock on Y, and since there is no lock on Y, transaction T2 can read on Y. Transaction T2 performed a read on account Y, and it received a value of 10 because at this point the transaction T1 has not performed any modification, and that is why we are like there is no modification happened, and that is why the amount of like value in present in y is 10. And this is what transaction T2 saw, and after that transaction T2 print the values, which was 8 and 10, and after that transaction T1 reached here and it performed manipulation on y. Performing the manipulation, adding amount of T to y, it became 12. And that's what the initial configuration was, x equal to 10 and y equal to 10, meaning there was a $10 amount in both account x and y. We withdraw amount $2, that is t, from account x to account y, and after that the configuration was 8 and 12. But here the problem is that the transaction 2 has seen a different value of account y because like it acquired a lock at a different state of time. So if we see the audit made by transaction T2, the total account balance is 18, but the total account balance at the end of T1 is 20, and initially the total account balance is 20 as well. So what has happened is that since we are moving the amount, right, since we are moving the amount from one transaction to another, and we are making like sure that that amount is moved within two transactions, the total should be constant, or the total amount should be constant, right? And that is why this value of 20 should be constant. But what has happened here is that the value has been changed to 80. So probably transaction T2, that is the audit transaction, would be wondering that what has happened, what went bad, that where is my $2 missing, because the amount was transferred from account X to Y itself. Then doesn't make sense, right? And that is the whole point of like this is the concurrency control we were talking about. Like this is the things which can go wrong if we like allow the other transaction to read the data item in the middle of transaction. About second case where again things can go wrong, if we allow one transaction to read in between of another transaction, or if we allow one transaction to read a data item which is currently in the middle of another transaction, or which is currently manipulated by another transaction which is currently in progress. So again we're gonna have do the same configuration. We have transaction T1 and we have transaction T2. Along with that, initially we have data item, we have account balances x and y. So x has amount 10 and y has amount 10, and we are trying to move an amount t which is 2 from account x to account y. That is what we are doing here. So initially again transaction T1 and T2 will be performing parallelly. So at the first step, what transaction T1 will do is that transaction T1 will move amount T from account X, and it will add amount T to account Y, right? And transaction T2 will read values. So it will read value from account X, it will read value from account Y. That's what we were doing. And now this time what will happen is that, so transaction T1 started its execution, it acquired a lock on account X, and it changed the value of account X, and now the value was modified to $8 because we deducted amount T, that is $2 from account X. Now T2 also started executing parallelly, but it reached at this point after T1, and since T1 has already performed over X, it released the lock, and now T2 can read the amount of X. So T2 read the account balance of X, and it found that the balance was 8. Now moving ahead, what happened is that at this point of time when transaction T1 was trying to read from account Y, there was some a network issue, or there was some machine failure. So since we mentioned earlier that account X and account Y was present in different machine, that's why this whole concept of distributed transaction. So the machine in which transaction Y, or the machine in which the account Y was present, failed or got shut down due to some issues, and that is why this transaction could not perform this operation. And if the transaction does not perform an operation, it does a rollback. So what it did is that it rolled back from here. So it performed a rollback, and since it is rolling back, it changed the value of X, or it undid the value of X from 8 to 10, so that our entire database is left in a consistent state, or left in the state which was like it was in before transaction T1 has started. So it did a rollback, and it undid the value of X from 8 to 10. But this transaction T2 does not know anything about it, that transaction T1 has rollback, and transaction T2 went ahead performing the operation. And when the transaction T2 reached at this point, this particular machine became active. So there was some machine failure that has happened, but after some time it became active when T2 went here, and hence it was able to read the value of Y, or the amount of balance present in Y. And what it read it to be obviously 10, because no change happened, right? Now after that it printed the values. So what transaction T2 printed is 8 and 10. So if we sum it up, we got 18. And what if we see at the end, what transaction T1 has is basically the account of balance of X is 10 and the account balance of Y is 10, since Y is left untouched. So if we sum it up, we got 20, right? And initially as well, the sum of amount in both the accounts was 20. So how did 18 came up? Again, while auditing, transaction T2 would be wondering that what has happened since the transfer has happened from one account to another. The sum of the amount in total in both of these accounts should be the same, should be unchanged. Then how this 18 is here? And that is another classical use case where not having a proper concurrency control can cause some data inconsistency. In conclusion, it would be safe to say that if our transaction would not have released the lock on the data items, right, in the middle of the transaction, then we would not have faced any of the above two situations, right? Because the above two inconsistency situation happened only because transaction T1 released the lock on account X in the middle of execution, and that is why transaction T2 was able to see that particular value of data item X in the middle of transaction T1, in the middle of the execution of transaction T1. And that was the issue here. So again, what we realize is that in case of distributed transaction, right, in case of distributed transaction, concurrency control is important. And what concurrency control says is that a transaction which is currently executing should hold the lock on the data item till its execution completes, right? So it should hold the data item until the transaction is committed, and only after that another transaction should be able to read the particular value of those data items. And that is the crux point of this episode, that what are distributed transactions and why concurrency control is essential in distributed transaction, and why, and if we do not take care of these things, then how things can go wrong, or how we can experience data inconsistency.